Hello, my name is Ben Fry. I'm a graduate student in the Ultrasound Imaging and Instrumentation Lab at Stanford University, and today I'll be talking about distributed aberration correction in liver imaging via iterative model-based sound speed estimation. One of the main motivations for the development of a distributed aberration correction tool is that overweight and obesity affect nearly 72% of US adults, 43% worldwide, and this global epidemic degrades image quality in medical ultrasound imaging due to increased body habitus, complicating accurate diagnosis. This is a problem because clinical ultrasound scanners assume a constant tissue sound speed. However, human tissue is highly non-uniform, causing ultrasonic wavefront distortion, which leads to beam mode defocusing, reduced lateral resolution, and a decrease in contrast. Here we can see an aberrated image from an ultrasound phantom shown on the left. We can see a corrected image shown on the right through an iterative aberration correction process. We can also see a decrease in the lateral full-width half maximums of these different wire targets between the left and the right shown by this bar plot. An unmet clinical need exists for improving image quality via aberration correction. Some recent aberration correction methods based on machine learning may utilize neural networks to train on raw channel data, for example, and use MSE, SSIM, or some other loss function to optimize the parameters of a neural network. Here, the goal is to produce aberration-corrected beamform data. Historically, neural networks struggle with out-of-distribution dataset errors, or they may produce uninterpretable or hallucinatory results. But especially in recent years, neural network models are built on well-documented automatic differentiation frameworks such as PyTorch and JAX, so they are easily customizable. Here we introduce differentiable beamforming as a network-free solution for aberration correction. In this method, all the components of the ultrasound image reconstruction and quality assessment are built using an auto-differentiation framework. This allows us to optimize some physical beamforming parameter, such as the local sound speed map, using an interpretable physical model. Because no neural networks are used, this approach does not require pre-training and instead uses an iterative optimization process to update the local sound speed map. I will now outline the differentiable beamforming model for aberration correction via sound speed estimation. First, we perform a full synthetic aperture acquisition of the dataset psi from a curvilinear transducer array. Next, we calculate a time of flight from a transmitting element to a point in space, RF, and back to a receiving element. This process depends on an underlying discrete grid representation of the local sound speed map. Therefore, our straight ray segments are interpolated onto this discrete grid. By integrating the slowness along the ray, we acquire a round-trip time of flight. We then use these time delays to perform synthetic aperture delay and sum beamforming, and we compute the common midpoint phase error image quality metric presented by Simpson et al. From our group. This result is used as a component in our loss function. Then we differentiate our loss function with respect to our initial sound speed grid values. We backpropagate these errors through our differentiable beamformer to update our initial sound speed assumption. This iterative process is repeated for a predefined number of iterations. We also made two additional changes to our differentiable beamforming model to accommodate curvilinear and experimental data. The first change involved determination of element normal directions to calculate a constant curvilinear f-number in Cartesian space. Here we can see a plot animating the constant f-number cone associated with each individual element. The color represents the time of flight to image domain positions. The second change involved using a phase screen model to apply timing offsets due to angular ray direction. This is to compensate for refraction caused by the lens used on physical or real transducers. The spatially varying flight time adjustment is shown for each element and is derived from an expression provided by Wasdorp et al. In their 2024 TUFFC journal paper on lens calibrations for improved sound speed estimation techniques. To demonstrate the impact of the physical lens correction, we validated our differentiable beamforming model using two calibrated phantoms for which the ground truth values were known. Without lens compensation, we observed sound speed estimation errors greater than 20 meters per second. Using Wasdorp's phase screen model combined with our method, we achieved errors less than 4 meters per second. We validated our aberration correction model on K-wave simulation and in vivo human liver data. We utilized K-wave in the quick ultrasound prototyping and simulation tool by Thurston Brevet to provide 4 simulation targets. We used a curvilinear convex array with the following specifications. The parameter layouts for our simulations involved a uniform, inclusion, quadrants, and IUS logo sound speed distribution shown on the top row. We chose a unique density map based on a natural image of a keyboard from the ImageNet collection to produce echogenicity variations in our simulation data. FSA and multistatic data was collected from K-Wave. For in vivo data, we used a Verisonics Vantage 256 ultrasound research system and a C52V convex array. We performed human liver imaging on 59 high BMI male and female subjects for a total of 375 acquisitions using an IRB-approved protocol. Starting with the aberration correction results on the K-Wave simulation data, we can see the delay in some B modes using a traditional 1540 meter per second sound speed reconstruction. Across all 4 targets, none of the keyboard letters are legible. Next, we swept over a range of sound speed values and found the value with the lowest common midpoint phase error to initialize each model with. The uniform 1650 meter per second result was initialized close to the ground truth value, resulting in fantastic aberration correction before any iterative process has been applied. The circular inclusion example was also initialized close to the background truth value of 1460 meter per second, resulting in good global correction. However, letters in the 4th row were not legible until the distributed aberration correction process occurred. The initialization of the quadrant example exhibits defocusing through all 4 rows. However, all 4 rows became legible after the iterative process. Finally, the IUS logo example shows similar initial defocusing in the 4th row that is resolved after the iterative process. All target B mode images are autofocused distinctly via distributed sound speed estimation. By distinctly, I mean that different samples may require varying amounts of aberration correction, which we will see next in the in vivo human liver data. Looking next at in vivo human liver data, we beamformed all 375 acquisitions at a global 1540 meter per second sound speed and plotted common midpoint phase error versus the common midpoint correlation coefficient. After performing k-means clustering, we found 2 distinct subsets of our data. Samples in cluster 1 had signs of high attenuation, poor acoustic coupling, reverberation, or other artifacts. These conditions impacted our aberration correction model and the sound speed estimations. Whereas samples in cluster 2 had cleaner signal and slightly lower initial common midpoint phase error. Pre-filtering of in vivo data enabled more stable sound speed optimization via differentiable beamforming. Our qualitative aberration correction is shown here using MimicNet, a neural network to make research ultrasound data look more like clinical data, to post-process our B modes. On the top row, we see a traditional 1540 meter per second reconstruction. On the bottom row, we will show the iterative process as an animation. The animation is not a traditional video over time, but rather over optimization iterations. For subject A, we see the artery feature become rounder and have a better definition. For subject B, while focusing on the middle feature, we see a clear increase in the definition of the feature walls in contrast with the background. For subject A, the anechoic vessel becomes darker and the boundaries become crisper. For subject D, we see the hypoechoic region become darker and rounder. All in vivo human liver B modes are autofocused, resulting in contrast and CNR improvement. Finally, we present quantitative aberration correction results on in vivo human liver data. For contrast-based metrics, we see that both contrast improved and CNR improved between the aberrated data, shown on the left, compared with the model-corrected data shown on the right. For global image quality metrics, we analyze common midpoint phase error, common midpoint correlation coefficient, speckle brightness, coherence factor, and lag1 coherence. Global image quality metrics improved by an average of 5.12%. However, due to the significant aberration in sound speed variations between subjects, We believe that better evaluation metrics would be useful for the assessment of sound speed-based aberration correction methods. In summary, we have designed and validated a differentiable beamforming model for distributed aberration correction that supports both linear and curvilinear arrays. We applied our model to in vivo human liver data from high BMI subjects. In vivo contrast and CNR improved by 2.75 plus or minus 3.28 decibels and 0.16 plus or minus 0.25 respectively. Global image quality metrics all improved. Due to the significant aberration and sound speed variations between subjects, better evaluation metrics are needed to assess sound speed-based aberration correction methods. I'd like to acknowledge funding through the NIBIB and members of the Ultrasound Imaging and Instrumentation Lab at Stanford University. I'd also like to thank Robin van Velzen for his excellent help on this project. Thank you for your time and interest in this work.